Hello, and welcome to the presentation of my work done over the last 10 weeks. During the course of this semester, I have worked on both research case studies as well as case studies on sustainable buildings. What has become clear through all of these case studies is that many users do not understand what makes a building sustainable. Many sustainable practices are approached like this today, specifically the work of Clifford. He looked at a thermal material called a PCM, which is typically embedded within a concrete wall. The user may be looking directly at the wall and not understand what makes that a sustainable practice. So my question is, what other sustainable practice can I make more visible in order to better educate the user? The HVAC system is a highly sophisticated system that takes up a large portion of a building's energy consumption. Rather than looking at the thermodynamic aspect of HVAC, as Clifford did, I wanted to look at another aspect, air purification. In my opinion, air purification and indoor air quality has become a huge issue for everyone. Many of us spend a majority of our day inside in a tightly sealed box in order to not let any precious conditioned air escape. But how good is this air that we continue to recirculate? While researching air purification, I came across an article by Gertner, and it really made me think, how does a tree clean the air? How does it pull the CO2 from the atmosphere? The answer is photosynthesis. A tree needs three things in order to perform photosynthesis: carbon dioxide, sunlight, and water. The carbon dioxide and sunlight are absorbed through the tree's leaves. The water is absorbed through the tree's roots and is transferred up through the leaves, and once it reaches the leaves, it combines with the carbon dioxide and the sun's energy to create the byproduct of sugar and oxygen. So absorption becomes an essential part of the photosynthesis process. I felt I needed to find a material that could absorb carbon dioxide, and I did just that. Klaus, Lackner, and Alan Wright discovered an anionic resin that can absorb carbon dioxide from the air and trap it within the material. I wanted to incorporate this into my air purification system because it addresses a key component of my strategy, but the material isn't perfect. The downside is that anytime this resin comes into contact with moisture, like humidity, the carbon dioxide will be released from the material back into the air. As a part of my research, I would want to perform some tests in order to find its limits. I would need to understand how much carbon dioxide the resin could absorb before it was full and needed to be washed clean, as well as what humidity level will the resin begin to release the carbon dioxide. Once I have a better understanding of the properties, materials, and limitations, I would construct some prototypes out of the resin. My initial idea, illustrated on the left, was to cut some shapes out of the resin and overlap them to create a visual interest. This would be purely aesthetic, I think, and I would need to understand what does this overlapping do to the performance of the resin. Lackner and Wright's idea was that they believed it performed best as rolled up into tubes and arranged like a bunch of straws. But why did they think the straws were the best configuration? I would need to perform another series of trial and error tests to understand what these configurations and any other configurations I came up with, how they limited the material, and which was the most productive. Tschumi says, most architects are blinded by form and ignore the potential of programs to generate forms. This really struck me because I realized I'd already decided what I wanted my air purification system to look like before I even knew how it would work. I had already had the idea that I wanted it to be some sort of wall system, so I needed to know how it would work. First, it would need to draw in the dirty air. Then, once the air is in there, the resin would extract the carbon dioxide from the air and trap it within the material. Then the clean air would need to be released back into the space. The resin does become full, and so we need a separate system that could rinse the resin and collect the carbon dioxide that was rinsed off of the resin and trap it as to not release it back into the air. This entire system would need to be enclosed somehow in order to not let the carbon dioxide escape. So here's my first attempt to fit that program into the form I'd already imagined. The dirty air would go into one end, the resin would then collect the carbon dioxide, and the clean air would come out the other side. the rinsing system would go from above and take advantage of gravity to run down the resin and be collected below. The biggest issue I have with this configuration is that the air would need to be forced through the system, and that would require a constant energy source. That defeats the purpose of a passive system. So I decided to try to take advantage of the stack effect. Here, the sun's energy would heat up this air within the enclosure, and it would begin to draw cool air in from the bottom, which would be the dirty air, and as the air passes over the resin, it could be cleaned, and the warm air forced out would be clean. This rinsing system would work in much the same way. Here, I just wanted to try to bring it more vertical from what we had before to take advantage so that the air movement and the rinsing system weren't trying to work against each other. Unfortunately, a diagonal doesn't have many architectural applications, and so I needed to address that. So I came up with this idea. It works much the same way as the previous configuration, but now it's a column, and a column would have many more architectural applications. It would also allow the user to view the system from 360 degrees. Here is a quick diagram of how I envision my system working. But I still need to make sure that my system can educate the user. In order to signify the collection of carbon dioxide, I would like to incorporate a color change property into the resin. I would think that when the resin was clean, it would start off as one color, and as it collects the carbon dioxide, it would slowly shift into another color. Once the resin is full, then the observer could witness the resin being washed clean, and it would go back to its original clean color. I also believe some signage would need to be involved to make sure that everybody who witnesses this understands exactly what's happening. So where would the system go? Because it's a building component, it could have a large and wide variety of applications, and there's no one specific building or site it could adhere to. It's important to consider your context for the building in order to find a good location within the building. The orientation of the system would need to be able to take advantage of solar radiation, but also would need to make sure that it would get good public viewing. So the diagram on the left illustrates that there's four different orientations that the buildings would take advantage of due to their surrounding context. On the right, we look inside of a building. I believe the systems highlighted in green would be the most effective because they're taking advantage of southern exposure. This would allow the stack effect to work optimally. Also, it's in a public space with lots of circulation, so it would be very visible to the public to view and reach the most people to educate them. The systems highlighted in red would probably be least effective, not only because they're not getting much solar radiation, but they're not reaching out to very many people. If the private space was located on the south, there might be an argument that the solar radiation would be more useful and you just may not reach as many people. So what? Why should we care? I believe that we need to educate the public in order to help them make better decisions. We cannot rely just on scientists and architects to make the world a better place. We need everyone to make a better place. So if they can understand what sustainability is and how it's working around them, they might be able to make better decisions in the future. Thank you.